This is the Kinematics Introduction. So this is the original question that we're going to ask ourselves. How can motion be described mathematically? And that's where kinematics comes into play. Kinematics is the branch of mechanics concerned with the motion of objects without reference to the forces which cause the motion and focuses on the four conditions of a moving object: time, position, velocity, and acceleration. So you can see that there is a graphic up there that shows a dot moving and it plots position versus time, velocity versus time, and acceleration versus time. Now, this relationship is where we get how we can calculate that. It all has to do with the graphs. So when graphing an object's position versus time, the slope of the line is the velocity. When graphing an object's velocity versus time, the slope of the line is acceleration. So if you think about what slope is, it's rise over run. So to calculate the slope, it's the change in the y-axis, delta y, divided by the change in the x-axis. So if we look at something like acceleration, there's the equation right there. It is the change in velocity divided by change in time, or rise over run, if you're plotting velocity versus time. So if you look at the graphs, if I'm plotting position versus time, the slope of this line, this top graph, is going to be the velocity. If I plot the velocity versus time, the slope of this line is going to be the acceleration. This is how those four conditions of motion interact with each other. And if we do a little bit of calculus and look at the slope of the lines, we come up with our kinematic equations. Now, don't panic. These are a lot easier than they look, right? So the arrow above some of the symbols means that they are a vector quantity, which means we have to take direction into account. The triangle symbol is delta, right, which means change in. So delta t is the time interval over which this motion took place. Delta x is the displacement or change in position. The subscript, those small variables at the bottom, indicate which direction or which velocity. So v0x represents the velocity in the x direction at time 0, right? When this time interval starts, the initial velocity, how fast is this object going? Vfx represents the velocity in the x direction at the end of the time interval, or the final velocity. So these are the variables, right? So we went over some of them, but v0x, that's the velocity in the x direction at the initial time, right? At time 0. Vfx represents the velocity in the x direction at the end of the time interval, or the final velocity. Ax represents the acceleration in the x direction. Delta t is the time interval over which this motion takes place. Delta x is the displacement, or its change in position. Now, here's the thing. You only need to know 3 of the variables in order to solve for all 5 variables. So here's how we use the kinematic equations. These are the questions that we need to ask ourselves. Which variable are you being asked to find? What 3 variables you already know? Which equation has those 4 variables, right? And then you can solve for that 5th one. And we'll go over how to do that later. So let's just do a quick practice problem. Just in Time accelerates his race car uniformly from 20 meters per second to 50 meters per second in 30 seconds. Determine the acceleration of the car during the time interval. Then calculate the displacement of the car during the time interval. So the first question we ask ourselves is, well, what variable is this? What are we being asked to find first? We're being asked to find the acceleration. Now we have to ask ourselves, what are the 3 variables we know? So we know the initial velocity is 20 meters per second. The final velocity is 50 meters per second. And the time interval over which this motion takes place is 3 seconds. So I'm going to go ahead and plug everything in there that I know. Then I need to look for the equation that has these 4 variables. Or I can take a shortcut and just look for the one that doesn't have the one that I'm not concerned with. Which one doesn't have delta x? So I'm going to use this top one, this top equation, and I'm going to plug everything that I know into the equation, and I can solve for the acceleration, 10 meters per second squared. Well, now I can find that last variable. Now, I can use any 3 of these equations to solve for it, but you can see here that third one, highlighted a little bit bolder, it's going to be a little bit better for us to solve, and here's why. Let's just plug everything that I know into this equation, right, and solve for delta x. It's 105 meters. Now, we would get the same answer if we use the second or fourth equation, but here's the catch. If I calculated the acceleration incorrectly on that first one, well, then I would calculate delta x incorrectly, right? But that third one doesn't have the acceleration, so we would be fine to solve it even if we got the acceleration incorrect. So now let's look at another one. I'm a Hurrian is approaching a stoplight moving with a velocity of 30 meters per second. The light turns yellow and Ima applies the brakes and skids to a stop. Ima's acceleration during the time interval is -8 meters per second squared. Determine the displacement of the car during the skidding process. Then solve for the time interval. So it's asking us to find the displacement. That's the first step. What are we being asked to find the displacement? Now I have to ask myself, what three variables do I know? I know the initial velocity, which is 30 meters per second. I know the final velocity, and this one's tricky. It comes to a stop, it's 0, and the acceleration is -8 meters per second squared. So now I can look for the equation that has all three of these variables, or sorry, all four of these variables. And here's the shortcut. Look for the one that doesn't have the one I'm not concerned with, delta t. It's going to be that bottom one. I plug everything in, and then I solve for delta x, and I'm going to get 56.36 or 56.3 meters per second squared. Well, now I can use any three of the other equations to solve for delta t, but I'm going to use the top one because if I use those middle two and I calculated the delta x incorrectly, I'm going to get that time interval incorrect. So I plug everything in, 3.75 seconds. So Ben Russian is waiting at a stoplight when it finally turns green. Ben accelerated from rest at a rate of 6 meters per second for a time of 4 seconds. Determine the displacement of Ben's car during the acceleration, then calculate the velocity of the car at the end of the time interval. So I'm looking for delta x, the displacement. That's what it's asking me to find. I know three variables. I know the initial velocity is rest. He starts at rest at 0. I know the acceleration, 6 meters per second squared. I know the time interval over which this acceleration took place. So now I look for the equation that has these four variables or the one that doesn't have final velocity, right? That's going to be that middle one. I plug everything in, and notice what happens to that first term, right? Because the initial velocity is 0, well, that first term is 0. I don't need to worry about that. And then I can solve for delta x, 48 meters. That's the displacement, the change in position. Well, now I can solve for the final velocity. At the end of this time interval, how fast is Ben going? So I look at all of these, and that top equation is what I'm going to use. I could use any of the other equations. It'd be fine. As long as I calculated delta x correctly, I could use those bottom two. The top one's just going to ensure me that I did it correctly, right? Or that if I got delta x incorrect, I could still get the final velocity correct. So I solve it, and it's going to be 24 meters per second, right? So we did the kinematics lab in which we were rolling marbles down a ramp like this, and we were timing it with the photo gate. So you can see that in that little thumbnail there. Now this is part 4. So there are videos for the whole kinematics lab, but I just want to go over these kind of problems, right? So what we did was we broke it down, and we were able to get our three graphs: the position versus time, velocity versus time, and acceleration versus time. And you can see here that the slopes of them are going to be, the slope of the position versus time is going to be different, which means my velocity is always going to be increasing, which means that it's going to have an acceleration. Now, one thing that we do go over is the fact that the slope of the velocity versus time should be constant, but the acceleration is not. And the reason is because the marble did not start at rest. Even though we started it like on a ruler and pulled the ruler away and it rolled down, it wasn't exactly at rest because it had to travel a little bit. That was just a systematic error, but as we moved the photo gates farther apart, that error had less and less of an effect on the actual time. And so we determined that the acceleration would be the 2.22 as it rolled down this ramp, and the ramp angle was 15.2 degrees. So that's where we got the acceleration for this problem, right? So this was part 4 where you calculated everything. So a marble accelerates uniformly at a rate of 2.22 meters per second squared. So we got that by identifying that systematic error and saying, well, where is the error not have the largest effect? For a displacement of 0.050 meters. That's very close. That's 5 centimeters apart. All right, this was that first lap. Over a time interval of 0.0924 seconds. This time was got from our photo gates, and the photo gate did have did have a resolution down to 1/10,000th of a second. And this was an average of 3 trials. So that's where we got that variable. Determine the velocity of the marble at the beginning of the time interval, then calculate the velocity of the marble at the end of the time interval. So it did have initial velocity that we do have to calculate because it didn't, we assumed it did not start at rest because it started up before the photo gate, right? So here's my initial, I'm solving for my initial velocity. I know these. I know the acceleration, which we calculated by doing different experiments. We got the time interval from the photo gate, and the delta x was how far those photo gates were from each other, and we got that from the measuring stick on the ramp. So I'm looking for the equation that has these four variables, or the one that doesn't have the the final velocity. So I plug everything in, and now it gets a little trickier because I'm solving for the initial velocity, and you can see here that it is like that first term isn't zero. So it does involve a little bit of tricky algebra, but you can get the initial velocity as 0.439 meters per second. Now I want to solve for the final velocity at the end. Now I can use any of these three equations. It doesn't matter. Now the reason why one of them isn't bolded, one of them isn't better than the other, is because initial velocity is in all of these equations. You have to know the initial velocity before you start any of these problems. That's the catch. So I'm going to use the top one just because, well, it's easier. So I just plug everything that I know into that equation, and you're going to get the same answer no matter what equation you use. That's what I want to get. Like, some students get mixed up and saying, well, I don't know which one to use. They're like, it doesn't matter. You're going to get the same answer. I'm going to use the top one just because it's easier, right? There's no way I can check that answer just because I have to have the initial velocity. I have to have calculated that correctly. And you can see that the final velocity when it hit that second photo gate, 0.643 meters per second, right? So that's the reason why I wanted to show this one, is because I wanted to show that you needed to know the initial velocity. So once again, there's just too much unknown in the universe to take a break from learning. Get out there and question everything.